When I gave this final at the University of Hawaii, we had the last friction problem, which we will not have on our final. And so to be able to cover both internal forces and frames, I combined them into one problem here. You will have just an internal forces problem, and then you will have a frame problem. So your problem on internal forces will not be as complicated as this. I had to make this problem kill two birds with one stone. It was a frame problem first, and after you got the reactions, then you could get the internal forces. Still, I will review both, but for your test, they'll be separate problems. Okay, first, the frame part of the problem. When you draw this free body diagram here, there will be four reactions: RAX, RAY, RCX, and RCY. You can't solve that because you can only solve for three reactions because you have three equations of equilibrium. What you always do in these cases, it'll be statically determinate. I will always put in an extra point that's like a pin, and that will give you another equation. So what I did was I sliced through the pin, and then I gave the class a choice: circle left or circle right. And so what we did was we decided to circle right. And then we drew that free body diagram. And so that's this free body diagram here. The key point is when you cut through a pin, you will have a shear and an axial, but there will be no moment. There is no moment at the pin. There was that distributed load. I took the area. The area of that rectangle is 1.5 height, 3 width. So that came out to 4.5 kilonewtons. And the unknown reactions at C. And what you do, you want to find a reaction. You don't want to find the shear or the moment. So what you do is you take moments about the point you slice through. So taking moments about B from this free body diagram 1, what I did, I took moments about there. So you have the 4.5 times 1.5. It's going clockwise, so negative. And you have RCX times 3 going counterclockwise, so positive. And solving for RCX, you get 2.25 kilonewtons to the right. And then what I did in class was I took that number and I put it into the original free body diagram. Now, if you look at this free body diagram, the overall free body diagram, there are only three unknowns: RAX, RAY, and RCY, because we know that RCX is now 2.25 kilonewtons. Once I knew that, I just did statics. I took sum Fx equals 0. I was able to get RAX. I took moments about A, and I was able to get RCY. And then I took some forces in the Y direction, and I was able to get RAY. Okay, so that would be the frame problem, which is problem 4 on your test. Now that we knew the reactions, we're going to do the internal force problem. And this part will be your problem 3. So the first part, which I just did, will actually be your problem 4, which I have another problem 4 on this practice test, so you get to see this twice. This problem, problem 3 on internal forces, will start here. Now, find the internal forces at D. So here is the frame with all the reactions drawn in. And in class, what I did was I took a slice and then I gave the class a choice. We can circle either left or right. It was about 50-50. It was a close call, but the majority voted to circle to the right. This would have been just as easy to circle to the left, but anyway, that's what we did. By the way, this 3 kilonewtons here, I should put in the units. Let me do that. Kilonewtons, kilonewtons, kilonewtons. that 3 kilonewtons on that leg was the area of this triangle here. You need to know that when you have a distributed load, the total load is the area. So that's a triangle. Its height on this side was 2 kilonewtons per meter. Its length was 3 meters. And the area of a triangle that's 2 high and 3 wide is 1/2 2 times 3, or 3 kilonewtons. And it's located at the centroid of the triangle, which is at 1/3 from the fat end or tall end and 2/3 from the 0 corner. So that was 2 meters from that side, or 1 meter from this side. That was a long explanation for this overall free body diagram. Now that we've sliced it and we have our loop, draw everything that's in the loop. And partly why we circled to the right is that it eliminated having to get that 3 kilonewtons on the left side correctly. Most people can find the area of a rectangle, which was 4.5 kilonewtons, and the centroid of a rectangle is in the middle. Okay, so I drew in everything that was in the green loop there, and what you slice through are an axial, a shear, and a moment. So there's an axial, shear, and a moment. I drew these in their positive sense. I told the class I would not take points off if you draw them in wrong. I just want the final answers correct. But before you get to mechanics of materials next semester, you really do need to learn that what I'm drawing right here are the positive senses for N, which is pulling, which is left on the left side, right on the right side. Shear, which is up on the left and down on the right, is positive. And moment. Smiley is positive, or clockwise on the left and counterclockwise on the right. These are all positive. And if you've noticed, I, out of habit, drew these 3 like that in their positive sense. Then I drew then I calculated sum Fy is 0. So V going up, 1.25 going down equals 0. V was positive 1.25 as drawn. I need to see this arrow. Okay. In fact, I'm going to ask you to redraw everything on a picture. There was quite a bit of discussion about this one. So N to the left minus N, 4.5 to the left minus 4.5, and 2.25 to the right equals 0. When you solve for that, N is minus 2.25, which is opposite of how I assumed, which means it's finally to the right. And we had a long discussion, like, no, it's this way or that way. Just look at the free body diagram. Finally, we took moments about D equals 0. I drew in the M as smiley, which is clockwise, which is kind of weird. It's negative for us because we take counterclockwise as positive. You had that minus 4.5 times a distance of 1.5 going clockwise. You had 2.25 times 3 going counterclockwise, and those two add up to 0, right? Because 2.25 is half of 4.5, and 3 is twice times 1.5. In fact, they definitely add up to 0 because that's how we solve for the 2.25 to make the moment up at that corner equal to 0. But we're not done. We still have that 1.25 going down. It has a distance of 1.5, so it is going clockwise, so negative, and M, solving for M, is minus 1.25 times 1.5, or 1.875 kilonewtons meters. Okay, I will ask on the test that you do this. You need to draw it in, redraw your free body diagram, and draw in the V, the N, and the moment. But this time, draw them in that correct direction of your answers. And so up, right, and counterclockwise.